What's up guys, it's Simon Fiaz and today's video is on optical isomerism question paper. Okay, from physics and math tutor. Before I continue with this video, I've got my mock starting next week, February 5th. So I'm going to try and get all these physics and math tutor question papers done before then, inshallah. And then after my mocks I'll be posting a mechanisms, practicals, past paper questions again and again. So, question 1. This question is about isomers with molecular formula. That I draw the skeletal formula with this, which is optically active. So, optically active is chiral carbon. So, if I've got a carbon, so if I go like this, and I've got this, and then the double bond O here. Perfect. Part B, describe how to distinguish between these. Well, this is just testing your knowledge really on optical isomerism. Obviously, your AO1 really. Use plain polarized light. And what happens, it rotates the plane rotates plane in opposite directions. Use plain polarized light, rotates in opposite directions. Draw the E and Z forms of a structural isomer of a space that shows both optical and geometric isomerism. So I've got, first thing I'm going to do is see carbon-carbon double bond here. Then I want an E isomer. So with E isomers, they are, what are they? The enemies. So I put a hydrogen here, and now just fill it in. So I've got a methyl group here, and then the remaining that will be here, CH3, OH. With the Z isomer, they're on the same side, so I can just put two hydrogens here on the same side. With this one, they were opposing each other, and then I'll just finish it off again. So CH3 here, CH3, OH. Part D says isomer G is this, has ether functional group, has only 3 peaks in its 13C NMR spectrum. Draw 2 of the cyclic isomers have an ether functional group and only 3 peaks in their 13C NMR spectra. And only 3 peaks. Perfect. Question 2. Prilocaine is used in anesthetic dentistry. Figure 1 shows the structure of prilocaine. Draw a circle around any chiral centers in figure 1. So chiral center has 4 different functional groups attached to it. So it is clearly going to be this one because it's got a C-O, it's got a CH3 methyl group, it's got an NH, and it's just got a H. So that's 4 different groups. Perfect. Part B, identify the functional groups in the prilocaine molecule. So I've definitely got an amine. Have got an amide? Yes, I have. Amine and amide. Ester, definitely not, because remember ester, it's like within ester, you've got the oxygen and then your R group attached to it. You have not got any of these like that. You're not bonded to a single oxygen. And ketone, yes, it's ketone. The carbonyl functional group is at the end of the carbon chain. It's not that. So it's amine and amide. Part C, draw the structures of two organic products forming a complete hydrolysis of this in acidic conditions. So, what I have to do is I have to cut off the link. So the link really is here. I've got this molecule and I've got this. Hydrolyze, so what's going to happen is I'm going to have the first one here. NH. I'm also going to have another hydrogen and another hydrogen. It's going to be positively charged. And then therefore the remaining one HO, positive charge nitrogen. I'm going to have HO, C double bond O, and then your remaining things. So CH, your methyl group CH3, draw out the individual hydrogen atoms, your NH, and then you just continue on. So CH, CH, CH3, so C3, 1, 2, 3, 4, 5, 6, 7, C3H7. Obviously, you should draw it out individually. In the example, I don't really have that much space. So yeah, you draw out CH2, CH2, CH3, but in this case, I just did C3H7. Part D says, explain how structural feature of this enzyme. Well, firstly, let's read this bit because there's a lot of information. Isomer F is an active compound in the medicine ibuprofen. In the manufacture of ibuprofen, both isomers F and G are formed. So both of these are formed. An enzyme is then used to bind to isomer G and catalyze its hydrolysis. After the products of hydrolysis of G are removed, a pure sample of isomer F is collected. Explain how a structural feature of this enzyme enables it to catalyze hydrolysis of this, but not the hydrolysis of isomer F. Well, first thing I want to talk about enzyme structural features. The enzyme has an active site. Enzyme has an active site. That's the easy mark. That's the first mark, the easy mark. The second mark is the more tough one. So what does that mean? Enables it to catalyze hydrolysis of isomer G, but not hydrolysis of isomer F. Well, isomer G must have the complementary shape. The enzyme has a complementary shape. Complementary shape. Now, obviously, this is a pretty tricky question because of how much information they're giving you, and it's a really unfamiliar context, right? But just think about it. How do you attack this kind of question? Structural features, enzymes. I know enzymes in A-level chemistry, it's not a lot of it, and it's just all about the active site and a complementary shape. Part 3 gives our UPAC name of this. So, first thing I can see is let's go aldehyde reacts with KCN followed by dilute acid to form a race mixture of the two stereoisomers of this. Now this is a molecule with OH and a C, and this is a hydroxynitrile. So that's going to be really important because I know I'm going to have to use hydroxynitrile. But now I need to figure out like the full name. So I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 carbons. hydroxy group is on the second carbon. That's the hydroxy group, OH group. So it's going to be 2-hydroxy, 2-hydroxy hexane nitrile. And this mechanism is an example aldehyde reaction. This is a nucleophilic addition. Yes, it is. Obviously, that's not really relevant to this question. But yeah, I guess it could be useful. This is nucleophilic addition. So 2-hydroxy hexane nitrile. Describe how you would distinguish between separate samples of two stereoisomers of this. Very, very similar to part B, 1B. Distinguish how you distinguish, and literally 2 marks, just a different example, a different context. Use plain polarized light. That's your first mark. And this is why it's really important to go through a lot of exam questions for topic, because there's only so many questions they can ask you. Literally, there's only so many they can ask you. Use plain polarized light, and what would happen is the enantiomers would rotate light in opposite directions. Enantiomers would rotate light opposite directions. Use plain polarized light, enantiomers will rotate light in opposite directions. Explain why the reaction produces a race mixture, 3 marks. Well, I've got the aldehyde, and what I need to know is that it's got a planar carbonyl group. So, planar carbonyl group, or you could just say planar. But what this means is that it can attack from either side. In this case, the Cn minus with the lone pair of electron, it can attack from either side, hence producing equal amounts of the 2 enantiomers, as with equal probability. You can say that instead. Part D, an isomer of this reacts with KCN followed by dilute acid. Dilute acid to form a compound that does not show stereoisomerism. Draw the structure form and justify why it does not show stereoisomerism. So this reacts with KCN. So it's obviously going to be nucleophilic addition. CH3, CH2, 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 CHO. So I know I formed this, but what I know is that it does not show stereoisomerism, therefore it's not got a chiral carbon. So I've got my carbon, I've got obviously a CN and a OH group, which they are separate groups. CN OH group, CN OH, and then I've got CH3 CH2, CH3 CH2 CH. Yeah, because this hydrogen can then go here. This hydrogen here, so CH3 CH2 CH. So CH3 CH2 CH2 CH3. Perfect. And then, but it also says justify. Well, this is a pretty easy mark. Does not contain a chiral center. Does not contain a chiral center. Or you could say does not contain a carbon attached to 4 different groups. I am supposed to do it there, but It's fine. Okay. Question 4: which pair of compounds? Obviously, in the exam, give you answer where it tells you to. Which pair of compounds does not form a racemic mixture when the compounds react? Now, I already know racemic mixture compounds react. It's going to be with either KCN, react with KCN, or HCN. One of the regions. We don't use HCl, so I can already eliminate A and C. Left with B and D. Well, the answer is going to be D then, because you can clearly see that it is a completely symmetrical ketone. Symmetrical, whereas this is obviously unsymmetrical. Symmetrical ketone. Symmetrical ketone. Remember, symmetrical ketones not going to have a chiral carbon. It's not going to form a racemic mixture when the compounds react. Which compound does not show stereoisomerism? 1,2-dichloropropene, 1,2-dichloropropane, 1,3-dichloropropene, 1,3-dichloropropane. So for the first one, A, 1,2-dichloropropene, methane, ethane. Methane, ethane, propene. I've got chloro on the first carbon, and I've got a chloro on the second carbon. 1, 2, 3. 1,2-dichloropropene. Let's check how many left. Okay, so quite a bit of questions left. Okay, which compound not show stereoisomerism? Well, I've got a double bond, 2 chlorine atoms on adjacent carbon atoms. So it actually can show stereoisomerism. It can show cis transisomerism. So restricted rotation is possible due to restricted rotation around the double bond. Propane, methane, ethane, propane, 1, 2, fill in the hydrogens. Is it got a chiral carbon, methyl group, chloro group, I guess, H, CH2Cl. Are all of those 4 groups different? Yes, they are. So that will show stereoisomerism. Propene, methane, see, same thing as before. CH3 here, chloro on the first carbon, hydrogen here, and I've also got a chloro on the third carbon. So in this case, I've got a chloro here. Now, does that show stereoisomerism? Well, I'll go look at the chlorine atoms. They're not directly attached. However, chlorine definitely has a higher MR than CH3, so it will take priority. So it will show stereoisomerism. Therefore, the answer must be D. And if I look at D, 1,3-dichloropropane, methane, ethane, propane, 1 chloro, 3 chloro, let's fill it in properly. Yeah, it's not got a carbon. These two are the same. So are these two. Answer's D. Question 6. How many isomers are represented by the formula C5H12? Just draw them all out and you should get 3. Name the type of structure isomerism shown by isomers of C5H12. It's going to be chain isomerism. Draw 3-dimensional representation of 2 enantiomers of 2-hydroxypropane nitrile. So I've got a carbon here, I've got an OH group, I've got a CN group, I've also got my hydrogen, I've got a CN group, I'll put NC here, and then here, and then the CN there. I've also got 2-hydroxypropane, so methane, propane, I need a H3C. And if I go here, carbon, OH, CH3, Cn, and this hydrogen is just here. Perfect. I think that the hardest part is knowing the full structure of 2-hydroxypropane nitrile, because the hydroxy, it's got OHCN, propane, gonna have 3 carbons, so we need to have a methyl group. Describe how separate samples could be distinguished. Again, very similar. Use plain polarized light. Polarized light. What happens? Rotated in opposite directions. Butane 2-ol reacts with concentrated sulfuric acid to produce 3 isomeric alkenes. Name and outline the mechanism. So it's going to be butane 2-ol alcohol reacting with concentrated sulfuric acid to produce an alkene. It's going to be elimination then. Elimination, and the mechanism. So I've got butane 2-ol. So methane, propane, butane 2-ol. So this is not really relevant to, I guess, optical isomerism, because this is year 1 mechanism. But you can see how they mix up topics. So what happens is lone pair of electrons, OH minus. In this case, elimination acts as a base, takes a proton, left carbon as a spare electron, wants to form a double bond. In order to form the double bond, COH bond must break. Therefore, I've got now CH3 CH. Obviously, it's taken this OH minus has taken this hydrogen, so there's no hydrogen there left. This hydrogen stays the same. This methyl group, CH3 group, stays the same. However, the OH group's left, and then we've got plus H2O plus the elimination. So wait, what is it with though? Oh my days, I just completely misread the questions. With concentrated sulfuric acid. So it's definitely going to be a very different mechanism. What happens we don't read the regions correctly? So ethane, propane, butane 2-ol, OH group is still going to be here, but in this case with concentrated sulfuric acid to form a mixture of alkenes, three isometric alkenes, what happens is the lone pair oxygen bonds to a H plus. Then you've got your, what happens here, CH3, CH2, CH3, you know, you just fill in the hydrogens, your hydrogen here. But now you've got your OH2 plus, where which one's positively charged? Oxygen positively charged. And what happens is it goes from the middle of this to the carbon. So it leaves. Then you've got your CH3, CH, CH2, CH3, H2, CH3, and what happens now is the carbon's positively charged. Now, let's form a double bond, and then you form either, in this case, you're going to form either butene or butene or butanone. And then it says explanation. 8 marks in total, so explanation. Loss of H plus from carbon and carbocation adjacent to positive charge carbon which OH was attached. From the first carbon, from I would just draw out leads to but-1ene, and then from leads to but-2ene, and but-2ene is formed as a mixture of E-Z isomers. And then question 7 says, which compound forms optically active compounds are reduction? So, reduction. Now, if I look at these compounds, I've got obviously CH3. I also got wait, what have I got? CH3 dual bond. Carbon CH3, carbon CH3 CH2 onto this carbon, I guess. Which one will form optically active compounds on reduction? Reduction. So I can reduce secondary The answer can't be A and B because they're both alkenes and they wouldn't form optically active compounds in reduction, so it must be B, C, and D, which are both ketones. But if I look at C, it's a complete symmetrical ketone. And symmetrical ketones won't form optically active compounds of reduction, therefore the answer must be D, and it makes sense because you've got your carbonyl functional group, and then you've got your CH3 here, and then you've got a CH3, CH2 here. Is that complete symmetrical? No, because these two are different. It's not completely symmetrical. Question 8 says, okay, can't really see it. Using knowledge of carbonyl mechanism suggests the name of the mechanism of this reaction. So now I actually do need to see it. So let's get rid of that. Hemiacetals and acetals are compounds formed by the reaction of aldehydes with alcohols, such as the reaction of ethanol with ethanol. So what happens here? Ethanol, aldehyde with an alcohol, it is going to be nucleophilic addition. Yeah, nucleophilic addition. And if you're not even completely sure, just go through, like, obviously you should know that this is a year 2 topic. Just go through like all the mechanisms in year 2, like write them down and be like, it can't be this one because of this, therefore you should get your final answer. But it is just 1 mark, so maybe do this at the end of the paper. Part 2, outline how an ethanol molecule reacts with ethanol molecule in the first step of this mechanism. So I've got this, we've got CH3, CH2, bond to the OH, lone pair of electrons, just like any other really mechanism, goes to the carbon, transfer electrons to here, and then it bonds to a H plus, and you know how the deal goes. That's partially positive, partially negative. You don't need to show that though, I don't think. Part B, explain the meaning of the term racemic mixtures. So a definition question. Equal mixture of enantiomers / optical isomers. Part 2, state the relationship between 2 chiral molecules with the same structural formula. 2 chiral molecules with the same structural formula. Non-superimposable mirror images. Again, this is just testing your AO1. Calculate the moles of ethanol, Kc, and then that's it. So almost there. This is applying Kc to optical isomerism. So it says the presence of acid catalysts such as dry hydrogen chloride, ethanol reacts with excess of ethanol to form an acetal. Overreaction is this: a mixture of this much of ethanol and this much of ethanol left to reach equilibrium. Equilibrium mixture contains this much of acetal. Calculate moles of ethanol in equilibrium mixture. So this is the way I like to do it. But before you even start doing this, you have to make sure that there's no algebra really involved. Like some questions, it wants you to involve x and all of that, but in this one, we don't need to do that. So I've got my acetal, which I'm just going to write as acetal. I've got ethanol, ethanol, acetal, and H2O, which I'll just write as H2O in this case. Now I'm going to use the ICE method. The ICE method, you write ICE. I stands for initial moles. So with ethanol, initially had 0.75. Ethanol, no, that's ethanol. Yeah, ethanol initially I had 5.00. Initially of acetyl H2O is 0 because it doesn't tell me in the question. Equilibrium mixture contain this much of the acetyl though. This is equilibrium moles. C stands for changing moles, E is equilibrium moles. So I can see the change is 0.42. And all of them, are they in a 1:1 ratio? Obviously that's a 2, that's a 1. But what about this to this? Yeah, that's gonna be a 1:1. So it's gonna be, that's gonna be 0.42, that's gonna be 0.42, 0.42, but that's not what we want to find out. So ethanol, I'm going to minus 0.42, and in this case, because it's 2:1 moderation, I'm going to minus 0.84. 0.75 minus 0.42, 0.33 for ethanol. Ethanol 5.0 minus 0.42 times by 2, 4.16. 0.33, 4.16. Then it says in a different experiment using the same reaction, equilibrium mixtures established at a given temperature. Mixture contain this much, this much, this much. I'm assuming it's equilibrium moles. Yeah, write an expression for the equilibrium constant Kc. Calculate value for Kc. Give units with your answer. So, write an expression for Kc. That's going to be nice. I think Kc. My product's a power of P over reactance to power of R. So it's just going to be. It's just going to be my acetal. I'm just going to write as acetal. Obviously, remember with Kc, it's square brackets. Acetal H2O divided by the reactance to power of R. CH3CHO times by CH3CH2OH. But because we've got 2 moles of it, it's going to be to the power of 2. Remember, square brackets, it's going to be squared. Then it wants me to calculate value for Kc. So, and I know the total volume is this, and I want it in, obviously I'm going to want to convert it into moles per dm minus cube. So that's going to be 0.31 or moles per dm minus cubed. And that's what I'm going to do. Is I need to show the calculation is 4 marks. So Kc is going to be square brackets acetal, and this is the equilibrium moles. These are equilibrium moles. 0.37 divided by 0.31 times by H2O water. 0.65 divided by 0.31 divided by CH3CHO, so that is the aldehyde. 0.58 divided by 0.31 times by OH, the alcohol, 3.76 of ethanol divided by 0.31. And remember, with the ethanol, it is squared. Now, one could argue that we don't actually have to divide them all by 0.31 because they will all cancel out. But it's better to be safe and just do it like this. Then you should get Kc as 9.1 times by 10 to the power minus 3. And the units, that final mark, the units, you don't want to get this mark wrong, you want to get it correct. Because usually it's pretty simple. Well, obviously I was working with moles per dm minus cubed for the, because concentration moles divided by volume, moles always in this, moles divided by the volume, moles per dm minus cubed. So it's going to be moles per dm minus cubed squared, that's products. Got 1 moles per dm minus cube here, 1 moles per dm minus cube, and the numerator squared divided by moles per dm minus cubed, because that's to the power of 2, that should be to the power of 1. So that'll cancel out, and I'll be left with 1 over mole per dm minus cubed, which is just going to be the opposite of that, so it's going to be mole to the power minus 1 dm cubed. Not mole to the power minus 1. Mole to the power minus 1 dm cubed. And then it says draw the structure of the acetal formed by a reaction of ethanol with ethane-12 diol. Draw the structure of this formed by a reaction of that with that. Acetal. So I've got carbon, O here, H, CH3. And sometimes for these reactions, if you're unstuck, go through the whole mechanism. Obviously, a lot of the time they're 1 markers, but still, you don't want to lose that 1 mark. So once you've done all the other questions, go through the whole mechanism. Obviously, if you don't know the mechanism, well then, you're just going to have to guess. And that is the end of this question paper, Optical Isomerism, Physics and Math Tutor question paper.